Good day, class. I hope you're all well. Welcome to another practice problem for our subject structural theory or theory of structures. Today we will mainly focus on the double integration method. Nabubulol agad. Okay, so we are to determine the equations of the elastic curve using the coordinates x sub 1 and x sub 2 and to specify the slope and deflection at point B where EI is constant. Okay, so class, this problem again is from the problem sets by Professor Hibler in his book Structural Design. So we are here to maximize our information and related concepts in order to fasten our learning curves. Okay, so here is our diagram and our illustration. We have a distributed load, a variable. In this case, W, okay? And then ranging from A to C with a value of A, okay? And the whole length of the beam is L, okay? So let's start. So first thing, again, our approach is to read the problems or to read the problem repeatedly until we understand what can we do and what can we accomplish from the given. Okay, so in this case, we have the following data with one loading only, a distributed load. Therefore, we can start simply analyzing what will be our reactions. So, initial solving. So, based on our statics, I will not elaborate this anymore. You will have a reactive vertical force and a moment resisting this distributed load. So, a positive moment to counteract the frowning face of the beam when it was subjected to this distributed load. So, that will be, the distributed load is equivalent to omega A or WA. Sorry about omega. That will be W in this case, multiplied by its length, applied at the center. Okay, at the center of this, of length A, so at A over 2. And the moment is simply, so as I said earlier, the moment arm is equivalent to the centroid or A over 2 multiplied by the value. So that will be a counterclockwise moment giving us a positive WA multiplied by the moment arm A over 2. So next, now we will have a proper again analysis on how we can approach this. So again, class, from the given, so let me repeat, we have the value x1 and x2. From this, we have an idea that you have to cut the sections at these points. Okay? So take note of that. That is very important. Cut the sections at this point. Okay? So in this case, at cutting section 1, boom. Okay, I'll be cutting first my section at x1. So here's my resulting diagram. And in order for me to find the moment equation, I simply need to get the moment at section 1, okay? At this point, okay? So once I cut this, I will have a resisting force or a vertical force upward and a counteracting moment. So let's call those reactions as V1 and M1, okay? So we can easily identify M sub 1 and V sub 1 from the section 1, okay? Next, we have here distributed load with the value again W. But the value had decreased because x sub 1 here is our length, not A, okay? Not A. Previously, it was A, but it was cut to x sub 1 only. Thus, our value is equivalent to W x sub 1. Okay? Next, it will be applied at a moment arm or at a length or at the center, x sub 1 over 2. So, I hope you get this. And then finally, our reactions. Now, this is based on our original function or original diagram. So, from our reactions in our statics computation a while ago. So, that will be VA is simply WA, and MA is simply WA multiplied by the moment arm a while ago, A over 2. Okay? So, summing up moments about point 1. So, that will be M1, here. Okay? Next. So, we're looking from left to right, right to left. Okay? So, this V sub 1, what will be the moment with respect to point 8, point 1? 0. Okay? 0. You have no moment arm. So, this doesn't give a bending or a flexure reaction. Okay? About point 1. Next, W x sub 1 moment arm x sub 1 over 2. So that will be this. Omega W x sub 1 multiplied by its moment arm. Y positive. So it's a counterclockwise. Okay, counterclockwise value. Next, adding up, what is this? WA multiplied by A over 2. So this is based on the, what is this? This is your moment, okay? The positive, okay? WA multiplied by A over 2, and then minus, what is this? So the moment with respect to this value, shearing force. So this is your moment arm, x1, with the force upward. So it will give you a clockwise moment, thus negative. So from your moment of equation, from your elastic curve, you can simply derive from the double integration formula. So I hope you remember this function, no? The moment function, x is equivalent to the second derivative of your elastic curve, where EI being constant. So, solving. Class, take note of this, no? M1, this is not M sub 1 multiplied to x. This is the moment function, okay? Just like in your algebra, f of x, so y of x, this case, m of x, because the moment varies with respect to x. So, moment is a function of x. Take note of that. So, in this case, since our value at moment, or we are concerned with the moment at section 1, here is our section 1 again. Moment function at x is simply these values. Okay, so this one coming from this value, I just transpose it to the right. Okay, so it became negative. This one, WAX1 from here, I just transpose it to the right, so it becomes positive. And then this one, again, from here, from your original moment at the cantilever support or the fixed support, so that will be WA squared over 2. So WA multiplied by A, WA squared divided by 2 over 2. Okay? So M1, that will be your moment function at x. So integrating both sides. Now let me change my highlighter. So let's use a yellow. Okay? So in this case, boom. Integrating, boom. Okay? And then, if you integrate this, okay, m sub 1, integrating that, will give you this. And integrating this one, will give you this. So, that will be my equation 1. So, I hope you remember your, your integral, okay? Sorry about this, no? So, M1 is also equal to this. So, this, integrating this one will give you the slope function. Integrating the slope function will give you the deflection function. So, this gives us our two unknowns, C1 and C2. Okay, so this is very basic, integrating each term. X sub 1 raised to 3, integrating that will be plus 1. So, magiging raised to the 4th divided by 4. So, that will be x to the 4th over 24. So, I hope you remember your double integration. Okay? This is your equation 1 and this is your equation 2. Next, cutting at section 2. So again, we have already the given. We have analyzed the given. We can simply analyze it or solve it by simply cutting at those sections. So this will be your new section at M2, giving me the reactions V2 and M sub 2. And then we are now going back to our original WA distributed load applied at A over 2 from C, since we have the centroid. And you have your reactive reactions from point A, from your cantilever support, giving us, since the original reactions from slide 1. So, let's solve. Take note of this. What is this value? Because it's very important, no? This value, this red line. Okay? So, that is your x2 minus A. Because we will be needing that when we solve the moment arm of WA with respect to point 2. So, let's look on this. That will be M2 plus WA x2 minus A plus, or since we'll start again from the right. Okay, from the right. So, summing moments at M2 is equivalent to 0, this one. So, that will be M2 positive counterclockwise. V2 is 0 since no moment arm from V2 to point 2. Then WA, ito na. So this is what I'm telling you a while ago. So that will be simply, the moment arm is simply x2 minus A, this length, plus this length, A over 2. So that's this one. X2 minus A plus A over 2. So this whole length. That is your moment arm. And this yellow line is equivalent to A over 2. Minus, what is this? What is this function? That is my original shear or vertical force from the cantilever support multiplied by the moment arm x2. Okay, this one. And then finally, my original moment from the cantilever support, WA multiplied by A over 2 counterclockwise. So solving further, what will happen in this equation? This is the same, okay? Distributing WAX to x2 will give us this function, right? So I can simply omit that. And then this one, take note of this. Negative A plus A over 2 will be negative A over 2, right? So once I distribute WA multiplied by negative A over 2, that is the additive inverse of this. WA multiplied by A over 2, positive. So positive WA multiplied by A over 2 minus WA over 2 multiplied by A over 2. Okay? So, canceling everything. Sana ganun din, no? Sa 2020, cancel everything. But do not cancel happiness. Okay? Do not cancel happiness. You deserve to be happy. Take note of that, class. M sub 2 will be simply 0. Okay? M sub 2 will be simply 0. Now, this is the long method, class. This is a very, very long method. I can also do that when I cut this section and take note of this beam, okay? Why did I teach first the hard? Because we will start again to the ideal. Before you run, you will walk. Before you walk, you will crawl. You will start with the basics. So I want you to learn the fundamentals first before we go to the easy part. Okay, so this is my cutting section 2. So, that will be giving me a vertical force V2 and M2, a reactive moment. But then I will not have any force from the right. Okay? From the right of section 2 now, in this case. So, cancel this. That will be M2 is equivalent to 0. Okay? That will be M2 equivalent to 0. So, from the elastic curve, again class, when you integrate 0 function, there is a value. Integrating this the elastic curve, okay, will give me a constant 3. And then integrating the slope function will give me the deflection function. Okay? So that will be my equation 3 and that will be my equation 4. So we're good. We have a series of equations and we can maximize also the boundary conditions. So from the boundary conditions, at x is equal to 0, in this case, in this point, okay, I will have no slope since I will have a fixed support. So my slope function is 0, will give me at equation 1 and at equation 2, C1 and C2 equivalent to 0. Okay? How about C3 and C4? How about C3 and C4? So the slope function is simply at point C, okay? Actually, at length A class, at length A, this is critical. X1 and X2 is the same, okay? When I assume at X1 and at X2, the slope function will be the same, okay? Take note of that. Because the values of, we have two independent variables, X1 and X2, but with the same value at A, the slope will also be the same. So we can maximize this continuity equation, giving us the following. So the slope function from equation 1 is equivalent to the slope function at V2. Now we know already from equations 1 and equations 3. Okay? So that will be equation 1. So this term, this whole function, equation. And then equate it to equation 3. So again, we know that C1 is 0. Okay, so this will, we are left with this. And that equating x to be A. Okay, and then you equate this to C3. What is C3? Okay, let's go back so we can recall what is C3. So this is just your basic C3. Okay, so that will be equation 1. Equation 1 is simply equivalent to equation 3. So that will be C3. So solving further, we are left with WA cubed over 6 negative. Now, another continuity equation at x is equal to A, you have the same deflections, okay, for x1 and x2. V1 and V2 deflections are equal. So C2 and C4, that will be simply equal. Okay? So equation 2 and equation 4. So this will be your equation 2. So we are omitting this class, E1, because it's variable. And then V1 and V2 are equal. So we can equate this function or these terms to this term. Okay, sorry about the highlight. Stabilo. Okay, so that will be at x is equal to A, we can simply have the following equation. So solving for C4, we have we're only concerned with C4 and one variable, two variables WA, but these two are from your given. Okay, so we will have C4 is equivalent to WA to the 4th over 24. Okay, so this is your deflection, class. This is your deflection. Okay, now finally our answers. So we are to find the slope at point B. Now take note, class, take note. The slope here is equivalent since at a very, very small deflection. So we are considering, I'm just looking at this, what you call this, exaggerated. But this is the same, okay? The slope will be the same. Okay, take note of that, class. So using equation 3, at slope B, that's simply WA3 over 6I 6EI. And then, solving for the elastic curve, we will have one equation and one unknown. Sorry about that. So, you can use the following equations. So, derived from the equation 4 or equation 1. Okay? So, sinimplify lang. Equation C4 and then equation 4 and then equation 2. Okay? So, am I correct? Okay. Correct. Now, let us look on this. What is this final term? So, V1 and V2 is equivalent if you look at X, start X sub 3 to the L. So, if you look from this, kaya pala may value ka dito. That's why you have a value here. Okay, X sub 3. So, if you look at that, like this term, no? So, let me highlight. Let's use a pen. So, if I reverse engineer, my cantilever support. So, this will be my new beam. If I look at this that way, this is my cantilever. Okay. And this is my distributed load. So, this will be my new length, X sub 3. If I look it that way, the deflections will be the same, giving us this function. Okay? So, that will be it, class. I hope you learned something regarding the double integration method. If you will have any questions, comment down below in this video or message me in my email or my Facebook account. Thank you all and God bless you all. For the love of learning is a way of life.